So we have two languages here, L1 and L2, and we will try to construct DFA for L1 and L2. So how do you construct a DFA for a given language? Most of it is intuitive. Like, let me take a page. So if the language is a power m, b power n, mn greater than 0. This is the language. So what are the strings that are a part of this language? The smallest string is AB, because m is greater than 0 and n is greater than 0. The smallest string is AB. And other strings are AAB or AABB, and so on. So it is an infinite language. So for an infinite language, your DFA will have a loop in it. We will see how. Okay, so there has to be an initial state. Let that initial state be Q0. Now you see, if your language has epsilon, in it, then the initial state will be final state also. Here there is no epsilon in this language, so initial state will not be the final state. Okay, now there are 2-3 approach that we are going to take to see how the things progress. Okay, consider these two. We want a to the power m, so we have to have a loop on the same state. What does this? By the time you reach Q1, the strings that you have scanned so far is A plus. What is A plus? A plus is basically A, so on, so on. So in this DFA, let's say M1, by the time you reach Q1, A plus is, by the time you reached Q1, for any string, if you have reached up to Q1, it means that the string so far traversed is A plus. And in this DFA, if you reach Q1, the string so far traversed is A star B. What is A star? Means that it is either A to the power MB or simply B. It means this is not the DFA for this language, because we want M to be greater than 0. So this is not the DFA for L1. The DFA for L1 M1 can become the DFA of L1. Depends on how we progress further in this direction. But this is not the direction that you should take to construct DFA for L1, because M is greater than 0, and so you cannot have A on Q0. You cannot have this self loop on Q0 at A. You must go from Q0 to Q1 first on seeing A, and then you can have a self loop on Q1. Similarly, once you have seen A to the power M, now any B that you see, you reach to Q2, and this will be the final state. You see as many B, it does not matter. So this is M1 is the DFA for L1. M1 is the DFA for L1. Okay, very good. So how do you construct DFA? It is through intuition. You get good in constructing DFA through practice only. For a given language, you can have any number of DFAs possible. This is one DFA M1 for L1. can we construct another DFA M2? So a small change in M1 and we have another DFA for L1 as M2. So a to the power m, b to the power m, and this is going to be a final state. But okay. There is one thing left. You cannot have dead configuration in deterministic finite automata. What I mean by dead configuration is you must have moves for every symbol and state. Means if your states are Q0, Q1, Q2 and your symbols are say A and B, for every state Q0 you must have move of Q0 with respect to A and move of Q0 with respect to B. So here you are giving a move where will Q0 go on seeing A, where Q0 will go on seeing B, it will go to a state, let's say Q3, and this will be a dead state. Why? Because the language does not start with B. If the language starts with B, definitely this string is not part of the language. So Q3 will be a non-final state and you will have A or B on Q3 will stay. Once your string enters Q3, it will stay in Q3, and that is why it is called dead state. Similarly, Q1 has moved for A and B both. Q2 has moved for B. Now, once you have A to the power m and B to the power m, you cannot have A. If in a string you have, let's say, A, B, A, it means this string is not a part of the language because it is not of the form A to the power m, B to the power n. It is not of this form. So, if you get an A, after you reach Q2, then that string has to be rejected. That string should not be accepted. So A can go to Q3. Okay. So let me make this page little neat and clean. So M1 is one DFA for L1, and we are constructing another DFA M2 for L1 with slight change in M1. Q1, it goes to A, B, Q2. Okay. So this is fixed. When it comes to the dead state, what we can do is for Q0, you have one dead state Q3. Q0, when it sees B, it goes to a dead state Q3. And Q2, when it sees B, it can go to another dead state, say Q4, A comma B. So for one language L1, you are able to construct two different DFAs for it. So we can have many DFAs possible for a given language. However, every DFA recognizes only one language referred as L of n, that we have seen in the last video. Now we will try to construct the language, the DFA for L2. And we cannot construct DFA for L2. Why? To construct DFA for L2, what is L2 here? L2 is A to the power m, B to the power n, such that m is equal to n. So L2 includes epsilon, AB, AABB, AAABBB. Means to construct L2, you need to maintain the count of A and count of B and check whether these two are equal. The number of A's is equal to number of B's or not. This functionality is not available in DFA. So to construct DFA for L2, we need to keep the count of number of A's and then compare it with B's. But in DFAs, at any point of computation, we are at one of the given state, and from that point onward, whatever happens for the remaining part of the string is independent of whatever we have seen earlier. So DFA does not have any storage. It has only finite number of states. And at any point of time, the next move of DFA depends upon what the current state and what the symbol is. Okay, so there is no way we can store that information. There is no way we can store the information of what number of A's we have passed through, and what number of A's and B's are there. So the only information that we have with us is what is the current state at which the DFA is, not more than that. So we cannot have any DFA possible for the language L2. So for L1 DFA exists, and for L2 DFA does not exist. L1 is regular, L2 is not regular. L1 is regular, L2 is not regular. To construct L2, we look at another automata, which is push-down automata. Push-down automata has an unbounded stack in addition to finite control and input take. And because of this additional feature, unbounded stack, we can construct PDAs for some languages which are not regular. So you can construct PDAs for the language for which you can give DFA. So for all those languages for which DFA exists, you can construct PDA for them also. You can also construct PDA for them. But even among the languages for which no DFA exists, there are still some of them for which you can give PDA. For all regular language, we can also construct a PDA for it. Therefore, PDA is more powerful than DFA because we can also construct PDA for many non-regular languages. So, if for a language L, if you can construct a DFA, then you can also construct a PDA. If you can construct a DFA, then you can also construct a PDA. If you can construct a DFA, the language is regular. If you can construct a PDA, the language is context-free language. Okay, this is your language L1 and this is your language L2. For the language L2, you cannot give DFA, means the language is not regular. But you can have PDA for the language, means the language is context free. So L1 is context free language, context free and regular language. L1 is context free and regular language, and L2 is context free but not regular. L2 is context free but not regular. All regular language is context free but not all context-free language are regular. Okay. So you can have a context-free but not regular language. You can have a context-free and also regular language. In fact, what is this regular? What is this regular language? Is a context-free language. So from here we get one more thing. What is that? Is that the PDA is more powerful? PDA is more powerful than FA, because there are languages for which you cannot give finite automata, but you can give a PDA for it. And this is how it is. But, okay, now look at this. Just as PDA is more powerful than DFA, there are classes of machines which is more powerful than PDA. And this pattern then follows. Like, if PDA is more powerful than FA, so we see that all regular languages context free, but not all context free languages are regular. So if, let's say, for example, Turing machine is more powerful than PDA. So for all the languages for which you can give PDA, definitely you can give Turing machines for it. But there will be some languages for which you cannot give a PDA, but you can give a Turing machine. And if there are languages for which you cannot even give a Turing machine, that language has no solution for its set membership problem. So similarly, we saw this for each class of machine, there will be another classification of language corresponding to that machine. And different machines and their corresponding class of language and relations between them is depicted in this not so pretty diagram. So if you have a finite automata, means if for a language you can give a finite automata, then those set of language is called regular language. If for a set, if you can give, look at this. This is regular language. 1 minute. Yeah. So this is for regular language. So for this regular language, you can give a finite automata. Okay. Similarly, whatever comes inside this circumference, are all context-free language, and for context-free language you can give a push-down automata. Similarly, whatever comes inside this circumference or this circle is context-sensitive language, and for context-sensitive language you can give a least bounded automata. And similarly, Turing machine. What is this area? This area means these are those languages for which you can only give PDA but not DFA. Similarly, this is the area which includes those languages for which you can only give least bounded automata but not PDA. And this is only those languages for which you can only give Turing machines and not LBA.